Congratulations! This live broadcast is specially brought to you by Academy YouTuber Malaysia, an initiative by eDidik Malaysia and Kelab Guru Malaysia. Please pay attention. The live broadcast will begin shortly. The link to the certificate of attendance will be provided at the end of the session. Please make sure it is filled within the stipulated time. Thank you.
Evening, teachers, parents, and all the wonderful students. Welcome to Pusat Tuisyen Academy YouTuber. Bermula percuma, selamanya percuma. How are you doing today? I hope all of you are ready for today's lesson. Before we proceed, let's begin our session by reciting a prayer for Muslims. The non-Muslims may pray according to your own religions. Okay, let me introduce myself. I'm Teacher Lau from SMK Tinggi Klang, the moderator of the day. We at Pusat Tuisyen Academy YouTuber will provide you with free online classes. Let's take this opportunity to do your revision. So are you ready? Let me introduce our teacher for today's lesson. We have Cikgu Shahnon from College Matriculasi, Pulau Pinang. We are now live on Cikgu Shahnon's channel. Please support his channel by clicking subscribe now. The topic of today's lesson is Atomic Structure Part 3. And together with us, we also have teacher Kong from College Matriculasi Perak, who is the control host. She's in charge of the smoothness of our lesson on technical support. We also have teacher Tang from College Matriculasi Selangor as our observer today to ensure the smoothness of our lesson. So before we begin, I have a few reminders to all of you. First, please pay attention to our lesson. Stop chatting and use the chat session wisely. Number 2, regarding certificate link, the link will be given at the end of our session. Please use eDidik account when you fill in your particulars and make sure to listen to the passcode given by me and fill in the form within the time limit, which is 30 minutes. So without, before we welcome teacher Shahnon, first I will give you the first three passcodes. A43. A43. Okay, so without further ado, let's welcome Cikgu Shahnon.
Assalamualaikum warahmatullahi wabarakatuh. Salam sejahtera. Good afternoon, all of you. Hope all of you are fine. And today is my turn. Okay, this is my poster. This is my poster, as you can see. And then this is my profile. My name is Shahnon from College Matriculasi Pulau Pinang. And my teaching experience is 21 years, and my channel is www.youtube.com/Shahnon channel. This is Kimia Prayu. Okay, we have a teacher Vivilau. Teacher Vivilau is our moderator today. Teacher Tang as an observer, and me as a leader for Kimia Prayu, and Cikgu Mawa and Teacher Kong as a host controller for today. And then this is mathematics Prayu, led by Teacher Im. Biology Prayu, STPM and matriculation, led by Cikgu Faiza. And Perakaunan dan Ekonomi Prayu, led by Madam Fizi. And last but not least, physics STPM Prayu, led by Madam Rosmaya. Okay, and this is our portal, Academy YouTuber Malaysia. Our portal, we can get more information from here, especially our you can get where is the okay tutorial here. You have we have category and so on. Okay, trailer, tutorial, PDC, and so on. So many things you can get from www.academyyoutuber.com. All right. Today lesson is actually continuity from Teacher Tang's. Okay, Teacher Tang's lesson, which is a Bohr atomic model. Okay, Teacher Tang not enough time to cover this ionization energy of hydrogen atom. All right, this is definition of ionization energy: the minimum energy required to remove 1 mole of electron from 1 mole of gaseous hydrogen atom at ground state. Okay, if you look at the ground state of uh, uh, hydrogen, electron will be at n equal to 1. Okay, and n equal to 1 we will refer to Lehman series. Okay, because ground state at n equal to 1, when the emission spectrum, we will refer to the Lehman series, right? So when electron at n equal to 1 absorb energy, gain energy, and excited to higher energy level, we call it n equal to infinity. All right, n equal to infinity. N equal to infinity means electron is removed from the atom. Okay, we already know that when electron excite to higher energy level, let's say at n equal to 3, the electron is unstable and will fall back to lower energy level. In this case, when electron excite to what we call infinity, then that electron cannot fall back to lower energy level because the electron is removed from the atom. Okay, so the Ni is the initial equal to 1 because we need the ground state. Okay, ionization energy refer to the electron at ground state, and the n final and f is infinity. So we will use this equation delta E equal to RH 1 over Ni squared minus 1 over Nf squared. And then the RH is 2.18 exponent negative 18, 1 over 1 squared minus 1 over infinity squared. And the answer is 2.18 exponent negative 18 joule. And this is for one atom. According to definition, ionization energy is 1 mole of electron. 1 mole of electron means 1 mole of atom of hydrogen. So we have to time with Avogadro constant 6.02 exponent 23, and the answer is 1312 kilojoule per mole. All right, this is ionization energy of hydrogen atom, 1312 kilojoule per mole. Okay. So summary for Bohr atomic model. Number 1 is electron move in circular orbit. About the nucleus, each orbit has a different energy level and energy state. All right. Let me zoom in. Zoom. Okay. And then the second one. The second one is in the specific energy level, the energy of electron is fixed in value or is quantized. The electron does not release or absorb any energy when it is in the ground state or at any particular energy level or orbit. And number 4 is energy is absorbed in the form of photon when electron move from lower energy level to higher energy level. Energy is released in the form of photon when electron fall back from a higher energy level to lower energy level. This is for a Bohr atomic postulate that you have to memorize this one. Okay. And then important equation for calculation. This formula was mentioned by Teacher Tang. At least 5 formula. 5 formula you have to memorize. Delta E equal to H nu. This one is new. In physics, nu is frequency. In physics, they will use F, frequency. In chemistry, we use nu or F. Okay? And delta E equal to Hc over lambda. All right, the nu of frequency equal to C over lambda. C is speed of light, 3 exponent 8 molar meter per second. Meter per second. Okay. Chemistry, always remember about molar. Molar, no. This is meter per second. And then H a Planck constant. Okay. And then we have E equal to RH over n squared. This one actually is this one. In a specific energy level, energy of electron is fixed in a value of quantized. So we will use this formula, E equal to RH, negative RH over n squared. The RH is 2.18 exponent negative 18 joule. Remember that we have two value of RH, joule for energy, and the second one is per meter for lambda, right? Okay, and then delta E equal to RH 1 over n I squared minus n F squared. The RH is 2.18 exponent negative 18 joule. Okay, E can be positive or negative. If we have positive means energy is absorbed by the atom. Negative means energy is released. Okay, this is formula of lambda, 1 over lambda equal to RH 1 over n1. Okay, and this one is n1 squared minus n2 squared. In this case, RH equal to 1.097 exponent 7 per meter. Okay, 7 per meter. Okay, don't get confused about this two value. Okay, for lambda, remember meter per meter. The unit is per meter. And for energy, look at the unit of RH, joule. Joule is for energy. And don't forget, for lambda, N1 must be less than N2 because lambda always positive. Okay? If you use N2 greater, N1 greater than N2, then you will get the lambda is negative. Okay? And we know that the lambda cannot be in negative form. All right. Now we look at the weaknesses of Bohr atomic model. Number one is unable to explain the line spectrum of atom or ions containing more than one electron. Okay, that's why we call it this Bohr atomic model. Bohr atomic model is hydrogen. Hydrogen only has one electron. Helium has two electrons, so we cannot use this formula. Okay, this formula we cannot use. Sodium, for example, we cannot use this formula. So sodium has 11 electrons. Okay, we cannot. This is the weakness of Bohr atomic model. The second one is unable to explain the extra line formed in the hydrogen spectrum. This is Balmer series in hydrogen spectrum, and between first line and second line, actually, it has an extra line. Okay, the line is quite thin, not very clear, but it's still a line. But Bohr cannot explain why it has an extra line. Okay. And number three is unable to explain the dual nature of electron. Okay, the dual nature of electron. The dual nature of electron actually proposed by de Broglie and also Heisenberg uncertainty principle. Okay, this is de Broglie postulate. Tiny particle like electron can also have wave properties. Okay, because electron is very, very small. So according to Broglie, electron also have a wave properties. Okay, and electrons should diffuse like wave. Okay, this is a wave properties in dimensionless space. And electrons should not be confined to a particular energy level. Okay, this is formula of de Broglie postulate. This is wave properties of wavelength, and H over m u. M is a particle mass of electron, very, very small, right? Very, very small. That's why particle like electron also has a properties of wave. And for Heisenberg uncertainty principle, it is impossible to know simultaneously both the momentum p and the position x of particle with certainty. And because of that, an electron should not be confined in a particular orbit because its exact position in velocity cannot be determined. This is what Heisenberg uncertainty principle um, uh, what we call say about electron. Okay, we can only determine the probability of finding an electron, and this is the formula of Heisenberg uncertainty principle. Delta x is uncertainty, we not sure in measuring the position. Delta p, uncertainty in measuring the momentum. Okay, uncertainty, everything is uncertainty. Okay, this is okay. Now we go to the quantum mechanical model. We have a terminology, atomic orbital. What is atomic orbital? Three-dimensional space around the nucleus whereby the probability of finding electron is the highest. Okay, this is the definition of atomic orbital. Very different with orbit in Bohr atomic model, right? Okay, as we can see, this is, let me zoom in a little bit. Okay, what we can see here is a dot here. The dot here is probability of finding electron according to this model. Okay, this is x-axis and y-axis, and this is probability of finding electron. And we can see here from this picture and this one, we have a different dot. That means different probability of finding electron. And look at here. Yes, we can see something that different. Okay, the third one is different from the second one. This is the probability of finding electron. And this is according to atomic orbital. Okay, atomic orbital, and the person that do all these things is Schrödinger. Okay, Schrödinger wave equation. Wave mechanics is mathematical model which can be used to define the probability of finding electron. Okay, and because of this, this person solve the equation use wave function. We have Trisula here, Trisula squared. Okay, wave function, and then the probability of finding electron and the shape of the orbital is resolved by Schrödinger wave equation. Okay, now we look at the quantum mechanical model definition. Number one, the definition of orbital. An orbital is a region in space around the nucleus where there is a high probability of finding an electron. Okay, this is definition of orbital. Remember, the etymology of orbital different with orbit, even though we just add al. Orbit and orbital different, right? Orbital, the term comes in quantum mechanical model. Orbit, the term in Bohr atomic model. Okay, and also the definition. We can see the definition, the differences between an orbital and orbit. And then each electron in an atom is characterized by four quantum numbers. Okay, the four quantum numbers N, L, M, and S. Four quantum numbers are useful to describe atomic orbital. We can describe atomic orbital and the probability of finding electron. We will use these four quantum numbers. Okay, what is N? N is principal quantum number. L, azimuthal quantum number or azimuthal quantum number, and M is magnetic quantum number, and S spin quantum number. Okay, N, L, M, S. Remember this? We have to use these four quantum numbers. Okay, we go to the first one, principal quantum number N. Okay, the name of number is principal quantum number. The symbol is N. And this is a symbol. This is the name, principal quantum number. Symbol. What is the number? Okay, we look at this first. Principal quantum number indicate the energy level and size of an orbital. Okay, and then n a positive integer. It starts from 1, 2, 3, and so on until infinity. Okay, this is the number of principal quantum number. Name of number, symbol, and this is the number 1, 2, 3 until infinity. N a positive integer. The larger the n, the greater the energy level, and the farther it is from nucleus. All right. So this is example of n. For example, n equal to 1. This is the size of orbital. And for n equal to 2, the size become a little bit bigger. And then n equal to 3, bigger than 2 and 1. And for n equal to 4, bigger than 3 to n1. All right. And also the energy also increase. Okay. N equal to 4, the energy is bigger than n equal to 1, 2, and 3. Okay, this is principal quantum number. More or less like orbit in Bohr model, right? Bohr model, we have n equal to 1, n equal to 2, n equal to 3, and so on. This is more or less like principal quantum number in Bohr atomic model. The second one is azimuthal quantum number or angular momentum quantum number. This is the name, this is the symbol L, and it indicates the shape of orbital. Okay, the shape of orbital. Value of L depend on principal quantum number, and it's depend on principal quantum number. For example, okay, yeah. Okay, for example, look at here. Zoom in. Example here. Okay. If n equal to 2, look at here, the L are from 0 to n minus 1. That means L only accept the number that less than n. Now, the value of n is 2. So L only accept number 1. 1 is less than 2 and 0. Okay, 0. So this is we can see that the L depends on n. Okay, if we know the n, then we will know the number of L. Okay. Okay, look at this. This is n equal to 2. For L, it will has two number here, 0 and 2. 0 and 1. Okay, 0 and 1, two number. Equivalent to number 2 here. Equivalent to number 2 here. Look at n number 4. N equal to 4. Okay, look at L here. 0, 1, 2, 3. Okay, we have 4 here. 0, 1, 2, 3. We have 4 equivalent to n equal to 4. N equal to 4. Right? And the number of L must be less than number 4. 3, 2, 1, and 0. All right. This is how we relate the L, the azimuthal quantum number, and principal quantum number. Okay. Then, okay, value of L generally designated by the letter SPDF. Okay, SPDF. Okay, let me zoom again. Okay, look in here. Okay, this is L equal to 0. L equal to 0. The symbol for L equal to 0 is S. Or we can call the orbital. This is L. S is orbital. This is S. The symbol is S, and this is the shape of S orbital, spherical. As you can see here, is spherical. Okay, and then 1 for L equal to 1. The symbol is P, and this is the shape of P orbital, dumbbell. Okay, dumbbell. And for L equal to 2, the symbol is D, and the shape is cloverleaf. Okay. And to make it more clear, look at the table given here. Okay, table: principal quantum number, azimuthal quantum number, name of orbital, and shape of orbital. Okay, let me zoom again. Yeah. Okay. For principal quantum number 1, the accepted number for L is only 0. Okay, 0 is less than number 1. Okay, look at 0 here, only one number, equivalent to 1 for principal quantum number 1. And the name of orbital is 1s. S1 refer to the principal quantum number, and S refer to the azimuthal quantum number. 0 is S orbital. So the name of orbital is 1s. And the shape of orbital is spherical. This is not circle. This is not circle. It must be spherical because definition of orbital is 3D, 3D space, right? The 3D space. Okay, look at principal quantum number of 2 here. Okay, 2. So the accepted number for L, azimuthal quantum number is 0 and 1. 0 and 1. For 0 is 2s. Okay, S 2 refer to the principal quantum number, and S refer to 0. And we have a 2p here. 2p, and the shape is spherical and dumbbell. And for 1s and 2s, 2s, the spherical shape must be bigger than 1s. All right. Okay, the same thing goes to the 3. 3, L equal to 3, no, N equal to 3. The L is 0, 1, and 2. 0, 1, and 2. So the name of orbital is 3s, 3p, and 3d. And look at the shape. For 3s, always spherical but different in the size. The size of orbital 3s always bigger than 2s and 1s. And also for 3p, 3p and 2p, 3p always bigger than 2p, 3p bigger than 3p. And this one is 3d, 3d is cloverleaf. A different shape from p orbital and s orbital. Okay, if any question, you can always ask the question on chat box, because I will not give any question. You can ask any question if you want. Okay, the third one is magnetic quantum number, M. Okay, magnetic quantum number. Magnetic quantum number indicate orientation of the orbital in space, okay, or indicate the orientation of the orbital. Possible value of M depend on the value of L. All right, this one good. Okay, we have N, we have L depend on N. Now we have M, magnetic quantum number. M also depends on L. So we have to look at L, and then you will know the value of M. Possible value of M depend on the value of L. For a given L, M can be negative L, 0, positive L. Negative L, 0, and positive L. Okay. Oops. Oops. Okay, this one. Okay. If L equal to 0, okay, L equal to 0, we refer to the S orbital, right? S orbital. M can only be 0 because negative 0 is 0, positive 0 is 0, and 0 is 0. So if L equal to 0, M equal to 0. Okay, mathematically, yes, this is right. And also chemically also right. Okay, L equal to 0, negative 0 is 0, positive 0 is 0, and 0 is 0. So the only number for L equal to 0, M only can accept 0. One orbital in S subshell. All right. For L equal to 1, M can be negative 1 because 1, negative 1 is negative 1, positive 1 is positive 1, and 0. Okay, and 0. 3 orbital. That's mean in p orbital, we know that L equal to 1 is p orbital. P orbital can has 3 subshell. Okay, we can see it as a 3 orbital in p subshell. If L equal to 2, so M can be negative 2, negative 1, 0, positive 1, and positive 2. 5 orbital in D subshell. If L equal to 3, lagi banyak lah. Okay. Okay. Look at this table again. Okay, we have a table here. And let me zoom in. Okay. Okay. For azimuthal content number 0, as we know that name or shape of orbital is S orbital. 0 is S orbital. And magnetic number for L equal to 0 is also 0. Okay, L equal to 0. And the orientation of orbital, because only one, we only have one orbital, so the orientation is at any direction. That's why the shape is spherical and the direction is at any direction. As we can see here, we will use 3 dimension. We have X, Y, Z. X, Y, Z exists. Okay, X, Y, Z exists, and the orientation is at any direction. For L equal to 1, this is P orbital. Okay, what time now? It's 31. Oh, I think I have to stop for a while because we have a tea break. Okay.
So thank you, Shahnon, teacher Shahnon. So before we go for advertisement, I give you the second number for the passcode, number 3.
Tuisyen online percuma. Tuisyen online percuma. Layari www.academyyoutuber bagi mengikuti tuisyen online secara percuma. Prasekolah, sekolah rendah, sekolah menengah, semua ada di Akademi YouTuber. Rujuk jadual di laman sesawang www.academyyoutuber.com. Semoga masa terluang anak-anak anda diisi dengan sebaiknya. Tuisyen online percuma, mestilah Akademi YouTuber.
Okay, teacher Shahnon can continue.
Okay, welcome back. All right. This is okay. Azimuthal contour number L equal to 1, and the name or shape of orbital is P orbital. All right. The magnetic contour number is -1, 0, and +1. As we can see here, we have a 3 number here: -1, 0, and +1. That means we will have 3 orbital. Okay, we have 3 orbital, and the orbital is Px, Py, and Pz. And Px, the orientation is at axis. The shape still dumbbell. Okay, the shape still dumbbell. We have a Py at y-axis, and for Pz at. That's why L, the magnetic contour number is defined as the orientation of orbital, right? You can see here Px, Py, and Pz. So we know that we have a 3 orbital, and the shape of orbital and the shape and also the energy level. Okay, the shape and the size of orbital are the same, but at different orientation. Okay, at different orientation of axis of X, Y, and Z. And for the L equal to 2, we refer to d orbital. Okay, this is d orbital. This one is quite complex. Okay, quite complex, because we have 5, -2, -1, 0, and +1 and +2. We have 5 orbital of d orbital, and the shape is cloverleaf. Yeah, cloverleaf, like a combination of dumbbell. Okay, 2 dumbbell combination at 5 different orientation. Wow, we only have 3 axes, and now we want to what we call, we want to write the 5 direction. This is quite challenging, all right? This is quite challenging. I think if I teach this one, I will take about 2 hours to finish how to show the direction or the orientation of 5 d orbital. Okay, so this one you can learn from your lecturers how to write. Okay, basically it has 5 5 orbital with 5 different orientation. Okay, we have a dxy. Okay, this one is dxy. Dxy actually the orientation is between x and y axis. Between x and y axis. dxy. Okay, dxy still globally. The orientation between y and z axis. dxz globally, and the orientation between x and z axis. Dx squared y squared, this orientation on the axis of x and y. And dz squared, the shapes we have like a dumbbell and a donut and a donut here. Okay, on z axis. All right. Okay, this is orientation. Okay, this is orientation. Magnetic quantum number actually we know the orientation of orbital. Okay. All right. The last one is electron spin quantum number. Electron spin quantum number. Electron spin quantum number define the spinning motion of the electron on its own axis. Only two direction, clockwise or anti-clockwise. And what is the number of electron spin quantum number? And the best thing about electron spin quantum number is not depend on L, M, and L. No? It's not depend on it. It just has two number, positive half and negative half. Okay, positive half and negative half. Maybe the positive half is the spin of electron is clockwise and the negative half is anti-clockwise. Okay, S can only have two value, positive half and negative half. Okay, and it's not depend on L, N, and M, right? All right. Okay, this is a bigger picture of N, L, until S. Okay, until S here. Okay, let me zoom in. Okay, look at here. Okay, let's say we have N equal to 1. This is N equal to 1. The L is equal to 0. The subshell designated is 1s. Okay, we already know this one. And the M, magnetic quantum number, is 0. The S quantum number is positive half or negative half. Okay. And then the number of orbital in subshell. Okay. The number of subshell, we will look at this M. Here we have only one number here, 0. 0 refer to the S orbital. So the number of orbital is 1. And maximum electron that can occupy orbital is 2. The maximum only 2. Okay. Whether is a positive half or negative half of electron. So we have here number of orbital in subshell. For N equal to 1, we have one orbital. Okay, what is the orbital? 1s. 1s orbital can be occupied by electron. The maximum number of electron, 2 electron. Okay, look at N equal to 2. Okay, this is N equal to 2. Principal quantum number is N equal to 2. And in N equal to 2, we have two number here, refer to the L. L is 0 and 1, and 0 we refer to the S, and 1 we refer to the 2P, and the magnetic quantum number for 2S is 0, and magnetic quantum number for 2P is negative 1, 0, and positive 1. Okay, this is spin quantum number. Spin quantum number for the electron, always positive half and negative half. Okay, positive half and negative half. How many orbital in 0? Only 1. Okay, only 1. And how many orbital in M here? Negative 1, 0, and positive 1, 3. So we have 3 orbital here, and total orbital is 4, 3 plus 1, 4. And total or maximum electron that can be occupied in this orbital is 8. Okay? 4 times 2, 8. All right? Any question? No? All understand? Okay. Okay, this one for n equal to 3. N equal to 3, we have 0. For L content number 0, 1, and 2, we have a 3s, 3p, 3d. Okay, this is a 3s orbital, and here 3p. Negative 1, 0, and a positive 1 actually refer to 3px, 3py, 3pz. Okay, negative 1, 0, and positive 1 refer to the orbital 3px, 3py, 3pz with different orientation, right? With same shape and same size, but different in orientation. And for 3D, this one, 3D, 3D, negative 2, negative 1, 0, positive 1, and positive 2, 1, 2, 3, 4, 5. Okay, we have a 5 orbital here. Okay, yeah, 5 orbital. And 5 orbital here, the name of orbital is 3dxy, 3dxz, 3dyz, 3dxy squared, and 3dz squared. Okay, you have to memorize all name of this orbital, and also you have to know how to draw the shape of orbital of D orbital. This one is quite challenging lah. Challenging to draw the orbital for S orbital and P orbital kacang putih. Okay, and then total of electron. Okay, we just sum up the number of orbital. 5, 9. Okay, 9 orbital times 2. So total number of electron can be occupied in n equal to 3. Orbital n equal to 3 equal to 18. So 2, 8, 18. Still remember form 4, form 5? 2, 8, 18, right? This one. All right. What time now? 40. Oh, okay, 40 minutes. All right. Now, we look at the shape of atomic orbital of. Okay, we look at S orbital first. As I mentioned before, spherical shape with the nucleus at the center. This is in the center. Actually, is the nucleus, and then this is the region where the probability of finding electron in S orbital. Okay, probability of finding electron. Spherical shape with the nucleus at the center. The probability of finding electron at the distant r from nucleus is the same from all direction. Okay, from all direction. When L equal to 0, okay, I've mentioned it. L equal to 0, we refer to the S orbital. As n increases, S orbital gets larger. 1s, 2s, and 3s. 3s bigger than 2s and 1s. Okay. This is p orbital. Okay, this is p orbital when L equal to 1. Remember that L equal to 1. N equal to 1, and then we refer to the magnetic quantum number. Magnetic quantum number, because magnetic quantum number actually refer to the orbital of P. Okay, Px, Py, and Pz. Okay, negative 1. The number, what is the number of magnetic quantum number? Negative 1, 0, and positive 1. The shape, dumbbell. Okay, dumbbell. The 3 p orbital, Px, Py, Pz, different orientation. This is Px. Okay, easy for us to draw the orbital. You just write the axis first, and write as the x, y, z, and then you can draw the shape, the shape of p orbital. Okay, we have a 3 different orientation, same energy, same size, same shape. Okay. As n increases, the p orbital get larger. Okay, we have a 2p and 3p and 4p. Of course, 4p bigger than 3p and 2p. And this one, this one is a d orbital. As I mentioned, p orbital. To draw the p orbital, d orbital, to draw the d orbital, it will take time. I think not enough time for today. Not enough time. I just give you the overview. Okay, when L equal to 2, so the number for magnetic control number is -2, -1, 0, +1, and +2. Right? We have a 5 number here. 1, 2, 3, 4, 5. This means we will have 5 types of d orbital, 5 types of p orbital with different 5 orientation. Okay, 5 d orbital with different 5 orientation. All right. This is dxy orbital. Okay, as let me zoom. Okay, dxy. Okay, look at the dxy. This is x and y axis. Okay, this is x and y axis, and then the d orbital dxy. Okay, as you can see, in between axis of x and y. Okay, in between. You have to know how to draw this. Okay, you have to know how to draw this. Okay, look at xz. You can see the difference. See different, huh? Okay, this is z, this is x, this is x. Okay, and then you have to draw in between axis of x and z. Okay, yz, yz in between y and z. And for x squared, y squared, this one easy for us to draw this orbital, okay, because the cloverleaf in the axis, okay, this is x, as you can see here, at the axis of x and y. And for z axis also easy, because in z axis, yeah, in z axis, and you just add donut here, just add donut here, and our dz squared orbital is ready to be eaten. No, this is not donut. We cannot eat this donut. Okay, still no question. Everybody khusyuk. All right. Okay, this is the last slide. Okay, okay. This is my question. The last slide for today. How many orbitals are there in 3D subshell? All right. Anybody? You can answer this question. How many orbitals are there in 3D subshell? Only in 3D subshell. How many orbital? Okay. Student, you can write your answer on chat box. How many orbital are there in 3D? Everything is quiet. Alright. Let's answer the question. Yeah, let's answer the question. 5.
One
Muhammad
answer
Khairul Azwan.
5.
Okay, 5. Good. Okay, 5. Let me write the answer. Okay, good. All right. 5. Only Muhammad Khairul, huh? Muhammad Khairul, huh?
Yes, only one answer.
The only one. Oh, where is my pen? Okay, my pen is here. Oh. Okay, the answer is 5, huh? Okay, 3D 5.
Haris also answer 5.
Muhammad Khairul 9. This is question number 2, huh? Okay, what is the maximum number of beetle that exists in the shell number 3? Shell number 3. Shell number 3, yeah? 9. Muhammad Khairul Azhar 9. Faris 5. Okay, shell number 3 is n equal to 3, right? Okay, n equal to 3. And n equal to 3, we want to know the number of orbital. That's mean orbital, huh? Orbital magnetic quantum number. Okay, in n equal to 3, we will have L. Okay, L here. I will put here. L here 0. Oh, I happened. 0, 1, and 2. And for M, yeah, M, we will refer to M. Nice. What happened to this pen? That can be baru. Okay, M is 0. This one is -1, 0, and +1. And for 2, -2, -1, 0, +1, and +2. So total maximum number of orbital. Okay, this is orbital. 1, 2, 3, 4, 5, 6, 7, 8, 9. Yes, Muhammad Khairul Azhar. Azhar. Nama Khairul Azhar. The answer is true. 9. 9 orbital. Okay, we have to refer to the question, whether it is 3D or n equal to 3 and so on. Okay. Which of the following orbital? Okay, we still have a lot of time. A lot of time. Which of the following orbital are allowed? 3D. Okay. 3D allowed or not? 3D. Okay, first A. 3D. 3D. How we want to know the orbital is allowed or not? We have to refer to the number here. 3D means 3 here. 3D. Okay, I write here. 3D. Oh, I have to change the. Let me change first the color. It's color. This one. Oh, highlighter. And the color is this one. Okay, 3D. Look at this one. 3D. For 3D, principal quantum number is 3. All right. D, we refer to the L. L for 3, 0, 1, and 2. For 0 is S, 1 is P, and 2 is D. All right. We have a 3 here and we have a D here. So 3D is allowed like this. 2F. Okay. No, B. 5S. For 5F, allowed. 5F. Okay, B. 5F. 5S. 5S. Is it allowed or? Sorry. 5S. Allowed or not? B. All right, we have Muhammad Khairul Azhar. A, E and F allowed. Only A and E. Only A and E. Okay. 5F is allowed because S, we will have S at any number. Okay, we will have 1S, 2S, 3P, 3S, 1S, 2S, 3S, 4S, 5S, 6S, and so on. Okay, if you see the orbital of S at any number, S orbital will exist. Okay, at any number. Okay, at any number. For P orbital, it will start with 2P. 2P. P orbital start from number P. D start from number 3. And 2F not allowed. 2F not allowed. 2F not allowed. Because look at 2 here. F. Okay. We have a 0. Only 0 and 0 and 1. 0 is for S orbital. 1 is for P orbital. Okay. Only S and P orbital are allowed in 2. we call it shell actually. 2 is a shell. So 2F is not allowed. 2 not allowed. G, 4G. G, let me padam dulu lah. Where is the answer? Okay, this one. Okay, this one is allowed, not allowed. 4G. Okay, yes, like this. 4 and L M. Okay, we start from here lah. 4G. L is 3 0. Let me erase it. Okay. Okay, the number is okay. The number 0 1 2 3 for M. Okay. This one is for G. This is for S. This is for P. This is 4D. This is 4G. Yeah, 4G is allowed. You just write like this and refer 0 to S, 1 for P, and so on. 4D. 4D. Okay. 4D allowed. 4D also allowed. You see here. 6F. Okay, 6. 6F. Okay, this is N. This is L0. Here, this is 4 already. Okay, 4. The orbital only until G. Okay, until G. That means no 6. Oh, this one is 6. Okay, let me erase this one. 4G. All right. 4F. 6. 6F. 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 So 0, 1, 2, 3, 4. No, not yet. Not yet. Okay, 4, 5. Okay, 5. Until 5, right? 0, 6. We refer to the 6. 0, 1, 2, 3, 4, 5. 0 refer to S. 1 refer to P. 2 refer to D. SPD, F, FG, and then H, okay, and then after that HIJKLMNOP. Okay.
Cikgu Shahnon.
So, yeah, 2 minutes. All right.
Look at.
Okay.
We
F.
look at.
Any F here? Yes, F. This is allowed. Okay, and I think okay, number 4.
Cikgu
Number 4 is
Shahnon.
the last one. Which,
Can we look at
yeah.
the 4G? It's a 4G, 4F.
4G. Oh, this one. 4G.
Yes.
4G is not. Okay, 4G. Okay, look at here. 4. This one. This one. This one is 4G. 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 4S, 4P, 4D, SPD. No, this is F. Yes, this is F. This is 4F. So 4G is not allowed. 4G is not allowed. SPDF, SPDF, GHI, and so on. For 4G, if you look at here, we only has 4S, 4P, 4D, and 4F. 4F, no G. So 4G not allowed. 6F, yes. SPDF, okay, allowed. Allowed. Only 3D, 5S, 4D, and 6F. All right, the last one. Which of the following quantum numbers are not allowed? Okay, remember, this is N, M, L, S. M depend on N. Okay, M must be less than 2. Okay, allowed. 1, the L number depend. This is L, this is M. Okay, M depend on L. positive 1, negative 0, and negative 1. Okay, allowed. Okay, this one allowed. B, 3, 0, 0 less than 3. Okay, allowed. 0, 0 same to 0. Okay, allowed. This one is negative halves because as the accepted number only negative half and positive half. That means for B also allowed.
We
C.
have an answer
Oh.
from Faris. C.
Answer from Farid. C. Okay, C. Farid. Okay, good. Which one is not allowed? Okay, C. C because the L number here same to the N number. This is not allowed. The L number must be less than N. Principal quantum number. Okay, this is not allowed. Okay, I think that's all for today. And of course, discuss will be continued by teacher Kong, teacher Kong next week. So don't forget to please come to our class for next week. So only that's all for today. Okay, that's all for today. Okay, go to the moderator.
Okay. Thank you, Cikgu Shahnon, for the interesting lesson. Before that, I give you the last passcode, number 1, last passcode for today. Okay. So with God's grace, we are done with today's session. We have learned a lot from Cikgu Shahnon about atomic structure. Congratulations to those who are able to follow our session from the beginning till the end. And thank you very much, Cikgu Shahnon, for such an interesting lesson. Before I provide the certificate link, please check the chat box for the certificate link. Please off the live chat button and click subscribe button if you haven't. This is to show your appreciation to Cikgu Shahnon for giving you a free lesson today. Don't forget to click the bell button too, so you won't miss out any new videos and live classes from Cikgu Shahnon. If you like today's class, then please click the like and share it to your social media friends. Let's share the knowledge you received today with them. Sharing is caring, right? Once again, I would like to thank you, Cikgu Shahnon, for the interesting lesson. Thank you also to Teacher Kong and Teacher Tang for being with us today. I think that's all for now. See you in another session. Please do remember, stay at home. Goodbye, everyone. Have a nice weekend.
Wow, banyaknya hadiah menarik menanti anda. Wah, kini Akademi YouTuber mengambil inisiatif baru di mana memberikan hadiah-hadiah ini secara percuma. Ya, percuma kepada anda semua. Bagaimana caranya? Dengan mengikuti kelas tuition online percuma Akademi YouTuber sambil mengutip mata kredit, anda dapat menukarkannya dengan hadiah-hadiah yang menarik ini. Tunggu apa lagi? Segalanya percuma. Jangan lepaskan peluang tau. Dah dapat banyak hadiah menarik, takkan nak lepaskan peluang. Layari www.academyyoutuber.com sekarang untuk maklumat lanjut.
Dibawakan kepada anda oleh Akademi YouTuber.